This is the 4.6 practice. Number one, we Christmas lights. We have 20 lights, and if one of them goes out, they all go out. Okay? So each light has a 96% chance of working for 3 years. So what's the probability that all 20 lights are going to keep working for the 3 years? Okay? So we want to take the first light has a 98% chance of working, and I want the next light to work, and the next light to work, and the next light. So I have to do 20 of those, right? So I want to multiply these together 20 times. Instead of typing all that out, it's easier to just take 0.98 raised to the 20th power, which is about 67% chance. Okay? So there's about a 67% chance that all 20 will work for the whole 3 years. Okay? Yeah, so one light has a very good probability of keeping working. All 20 lights altogether, not as good of a probability. Okay, so the next one, a certain lie detector will show a positive reading indicating a lie 10% of the time when they're actually telling the truth. So there's an error there. Suppose we take 5 people and they give them the test, and they're all telling the truth. It's a probability of no positive readings. Okay, so if they get a positive reading 10% of the time, they don't get a positive reading 90% of the time. So we want 5 people to not get a positive reading. So 0.9 times 0.9, 0.9, 0.9, okay, which is 0.9 to the 5th, which is 0.59. Okay, number 3 for you guys. Type O blood are universal donors, and only 7.2% of people in the U.S. are O negative. So if we choose 10 Americans at random, what's the probability of at least one of them is a universal donor? Okay, so at least one is a universal donor. So remember how if we have at least one, okay, we're taking 10 people, so either 0 people could be a universal donor, or 1, or 2, or 3, or 4, all the way up to 10. I want to know at least one, so I want to know this probability right here. But instead of finding each of these and adding them together, let's find this one and do 1 minus this one. Okay? Okay, so the probability that no one out of 10 is a universal donor. So if a universal donor happens 7% of the time, we know they're not a donor, universal donor, 92.8% of the time. Okay, and I want 10 people not to be a universal donor. So I want to do 0.928 to the 10th power. Okay, that's the probability that no one is out of those 10 people, no one's a universal donor. And then I do 1 minus that, and you get 0.5263. Next problem, a shipping company claims that 90% of its shipments arrive on time, which means 10% are late. Suppose that the claim is true. If we take a random sample of 20 shipments from a company, what's the probability at least one is late? So once again, kind of thinking about this at least one idea. I could have 0 late, or 1 late, or 2 late, or 3 late, or 4 late, or 5 late, all the way up through the 20 packages. And if I want to find this probability, I'm going to do 1 minus that probability. Okay, so what's the probability that none are late? Okay, so the probability that none are late. Okay, so if that's probably on time, the probability it's late, well, it'd be 10%, but we're going to know if none late means they're all on time. So I want to know probability they're all on time. So I want all 20 packages on time. So I want to take 0.9 times 0.9 20 times, which is the same as 0.9 to the 20th power. And I'm going to do 1 minus the probability that they're all on time. Okay, so the probability comes out to be 0.8784. An airport reports that 85% of its flights are on time. So if I take the next four flights coming into the airport, what's the probability they're all going to be on time? So can I take 0.85 times 0.85, right, for all 4 of them? Why not? No. So we can only do this if they are independent, right? If one flight does not affect the other. But I think if we take the next 4 flights, if the probability of the first one being being late is probably like if this one has a higher probability of being late, the others would also have a probability of being late. So I think that they are all they're not independent. There might be a weather event, it might be snowing, so this one's going to be late, and those other ones would also be late as well. Okay, what's happening with the weather and other events has an impact on all the flights, not just one of them. Okay, so they're not independent is the main idea there. Okay, so in a big, large building, 40% of the residents read the USA Today, 25% read the New York Times, and 5% read both. Suppose we picked a random person. Event A is they read the US Today. Event B is the New York Times. Are they independent? Or does knowing one thing about somebody affect the probability of the other thing happening too? Okay, now if they are independent, we know the probability of A and B would equal the probability of A times the probability of B. Okay, probability of the USA Today was 40%, probability of the New York Times is 25%. If I multiply those together, I think it's 0.1. That is not equal to the 5% that read both, which means they are not independent. Since they're not equal, they are not independent. If someone gets one newspaper, there's a bigger probability that they will also get the other newspaper as well. Okay, last one, number 7. Many fire stations handle more emergency calls for medical help than they do for fires. At one fire station, 81% of the incoming calls are actually just for medical help. Suppose we choose 4 incoming calls at the station. What's the probability that all 4 calls will be for medical help? So I want the first one to be for medical help, and the second one be for medical help, third for medical help, and fourth for medical help. So that's 0.81 to the fourth, which is 0.43. Part B, what's the probability of at least one of the calls is not for medical help? Okay, so if you think about probability at least 1, okay, so I could have 0 for medical help, 1, 2, 3, or 4, right? So at least 1, I want to find and use that 1 minus, right? So the probability of at least 1 for not medical help would equal the probability of 1 minus that all of them were medical help. And all of for medical help was a 43% chance, so 1 minus that would be 57%. Part C, explain why the calculations in Part A may not be valid if we choose 4 consecutive calls, okay, to the station. So if there are 4 consecutive calls, one right after the other, they might not be independent. The one call, the higher probability, like if something's happening around town, like we just had that explosion in town, right? So the next 4 calls might not be independent of each other. It might be all associated with the one event. So certain type of call probability may not be similar. They're not independent events.